Gases have four main properties that they need to characterize their behavior. P is the pressure, V is the volume, T is the temperature, and for it to be proportional, it has to be in Kelvin, and then N is the amount of gas, and that is given in moles. Historically, these properties have been studied and found to have certain relationships to each other. So it was found that pressure is inversely proportional to volume, that volume is proportional to the Kelvin temperature, the pressure is proportional to the Kelvin temperature, and the volume is proportional to the amount in moles. This is work done by Avogardo. That is how the number for moles got named after him. So we use that number for the amount of things. So this approach, they would study two different properties and how they're related. And then overall, we can summarize this in a combined gas law, combining all these different relationships. From our point of view, I think that one approach that might be easier for students is to start with this combined gas law when you have a gas law problem to look at, and then take a look at which things you're working with in the problems and which things are not mentioned. You might have a problem that mentions pressure and volume, but does not mention moles or temperature, and so it's assumed that the moles and the temperature are staying the same throughout the problem. And if that happens, if moles and temperature are not mentioned, then they're equal to each other and you can cancel them out, and then you can end up with the variables that you are going to work with. And so when you cancel out the temperature and the moles, you end up just left with the pressure and the volume, and this is the equation, and this is actually Boyle's law. It doesn't matter if you don't memorize which name goes to which equation, as long as you can come up with the equation that you have to use. If it's easier for you to memorize the equations separately, that's okay. I just thought that memorizing one equation and then crossing out what you don't need might be a way that works for a lot of students. So sometimes I recommend that. So all of these types of equations are used when you have a set of conditions set one, so an original pressure, an original volume, etc., and then you change something, maybe you increase the pressure, maybe you increase the temperature, and you want to see how the other properties change in response to that. So that's the kind of problem where you would use these equations. Let's give it a try here. All right, so it looks like we have a pressure and a volume to start with, so we'll call this V1 and P1. And then it looks like we have a change in pressure, so we have a P2, and that's all we have. So we do not have any moles or any temperature to work with. We're just working with this equation, the Boyle's law. And then when we insert our values for that, we come up with this equation. We can divide both sides of the equation by 33.65 inches of mercury. Then on this side, we will get V2 alone. On this side, the inches of mercury will cancel so that we end up with milliliters, which is encouraging if we're trying to find the volume. And it looks like the volume is 334 milliliters. One thing I always forget to do ahead of time, which is sometimes helpful for students, is to make a prediction. So if you look at this problem that you have a certain volume at 24.78 inches of mercury of pressure, we're increasing the pressure. So intuitively we can expect that when we squeeze down on something and increase the pressure, the volume is probably going to get smaller. So if you wanted to, you can make a prediction that the volume should be smaller, and then when you come up with this 334 milliliter volume, you can be encouraged by the result that it is smaller. So if it came out to be bigger, you might want to take another look at what you had done. So let's try a prediction for this second one at least. We add 0.0407 moles of gas to a balloon, and it takes up 884 milliliters of space. And now we're going to increase the amount of gas that's in there to 0.0732 moles, and figure out what the volume should be. All right, so we're going to make a prediction that if we are adding more gas and increasing the amount of gas, I'm going to predict that it's going to be a larger volume. So there is my prediction. All right, here is the combined gas law. It looks like we are just working with moles. We have N1, we have N2, and we have this. This is V1. We don't have any temperatures and we don't have any pressures. So let's cross those out. So this is what we are left with. It looks like we are going to be using Avogadro's law. And when we insert the values here, this is what it looks like. To get V2 alone, we're going to go ahead and multiply both sides by 0.0732 moles. So that is going to get V2 alone on this side. On this side, the moles are going to cancel, and we'll be left with milliliters. Again, that's a good unit for volume. And I end up with 1,590 milliliters as V2. This is in fact larger than 884 milliliters, so that is definitely a good sign. We have a little note down here. These kinds of problems, a lot of times it doesn't matter what units you use for the volume or the pressure, because these volumes are canceling, even the moles. We have the moles canceling, we have the inches of mercury canceling up here. But we have to have a temperature scale that is proportional. So something that doubles when you double the value. So if you double the pressure, it doesn't matter whether the pressure is in inches of mercury or millimeters of mercury or kilopascals or atmospheres. Those numbers are all proportional. They go down to 0. They don't go into the negative scale. And so if you double that number, it's going to double the pressure. But for temperature, the Fahrenheit and the Celsius scale have negative numbers. And so we know that they're not proportional to this measurement of temperature. If you have something that is negative 10 degrees Celsius, and you double it, like you make it twice as hot, you can't say that it's negative 20 degrees Celsius. So this only works with Kelvin temperature scales. None of these formulas are going to work if you use other temperature scales because it's just not proportional. The thing is that a lot of times we do see temperatures taken in Celsius. It's a very convenient measurement to take. Just remember that when you're using it, you need to convert it to kelvins. Okay, so here is our combined gas law. We are going to work with something that involves temperature this time. So here we have a volume of 1.87 liters, a temperature that we do not know, a volume of 2 liters, and a temperature of 24.2 degrees Celsius. If you had made this V1 and T1 because these are kind of the original conditions, that's okay, as long as you keep them on the same side of the equation, as long as the subscripts match, because these do match, then that should be fine. So we are not working with any pressures or with any amounts of gas. We are working with Charles's law over here. All right, before I insert the values into this equation, I'm going to go ahead and make sure that I have the temperature in kelvins. So if you make a list of all the values over here, that's sometimes helpful. Then any temperatures that you see, you can convert them to kelvins. And remember, this is adding, and we go 1 past the decimal. So when we add this, we can keep 1 past the decimal. So I'm going to make this 297.4 Kelvin. Now I'll go ahead and insert the values. I'll just put T1 here because we don't know what that one is. All right, so we want to solve for T1, not 1 over T1. If we divide both sides of the equation by 1.87 liters, we will not get T1 alone. We will have 1 over T1 alone. So I'm going to get T1 in the numerator first by multiplying both sides of the equation by T1. Okay, so now I have T1 in the numerator. I need to get it alone. I'm going to do that by multiplying both sides of the equation by 297.4 Kelvin and dividing it by 2 liters. That's going to cancel the 2 liters and the 297.4 Kelvin. Let me do that to this side as well. So now I have this equation here, and the liters are going to cancel. I'll end up with Kelvin. So this temperature comes out to be 278 Kelvin. And if the temperature were requested in Celsius, or if this is a multiple choice and the choices are in Celsius, we can convert this to Celsius by subtracting. We only know to the ones place. So we get 4.85, and we're going to have to round this to just 5 degrees Celsius. So I'll put those answers over here so that I can have some room to work with this problem. All right, so this original sample of gas, we have a volume of 3.42 liters, and the pressure is 1.42 atmospheres, and it looks like the temperature is 31.8 degrees Celsius. And then the new temperature is going to be 18.5 degrees Celsius, and the new volume is 4.13 liters. Okay, so we don't have the moles. We're not going to need that one, but we're going to need P1 V1 over T1 equals P2 V2 over T2. And before I insert those, I'm going to go ahead and convert these temperatures. And so we have 305.0 Kelvin and 291.7 Kelvin. When I insert all of the numbers into the equation, it looks like this. Then to get P2 alone, I'm going to have to multiply it by 291.7 Kelvin and divide by 4.13 liters. On this side, that gives me P2 alone. And on this side, it just cancels some units. The kelvins cancel and the liters cancel, and I will end up with atmospheres, which would be an appropriate unit for the pressure. I'm coming out with 1.12 atmospheres as the pressure. So one of the things that the combined gas law is telling us is that the pressure times the volume divided by the moles divided by the temperature is always the same. So this first set of conditions will be the same as the second set of conditions, which will be the same as the third set of conditions, and so on and so on. So the pressure times the volume over the moles times the temperature is always going to be the same value. And so what we can do is figure out what that value is, and then we can use that for problems where there aren't two sets of conditions. If there's just one set of condition and we just know what this value is, then we can find a missing value. If one of these four, P, V, N, or T, is missing, we can find it using the other three and the known constant. And this known constant is called the ideal gas constant, and it's represented by a capital R. So this is a common one that you will see a lot, especially when you use atmospheres as the pressure. This is when we have liters and atmospheres for the volume and pressure units, and then moles and Kelvin are pretty typical for the amount, and Kelvin is really required for the temperature. So the moles and Kelvins on the bottom is always the same, and then we have different ones depending on whether you are using millimeters. There's a different one. We're going to be using this a little bit later on in the chapter because this kilopascals is the SI unit, so it helps to relate the pressure to metric units like newtons and meters and kilograms. So this one is really useful also. So let's take a look at how this is done. We'll try a problem here. So we have a certain volume of hydrogen gas, and the temperature, we know the temperature. and we know the pressure, and what we are trying to find is the number of moles. All right, so all of these values for R have liters. So I'm going to go ahead and convert this to liters. This is 0.274 liters. And the temperature, of course, always has to be in Kelvin. So we have 296.4 Kelvin. We can keep this in millimeters of mercury as long as we use this value for R. If we use a different value for R, we're going to have to change the pressure either into atmospheres or kilopascals. So let's go ahead and use this value for R. And we have PV equals nRT. What we are trying to solve for is N, and so that would be PV over RT. So let's go ahead and insert those numbers. And so for R, we're going to use this one that has 62.36 liters times millimeters of mercury. And then instead of putting a slash here, I will just use this line that's already here. If something's in the denominator of the denominator, it's actually in the numerator. So I'll put the moles and the kelvins up here in the numerator. And then our temperature is 296.4 Kelvin. So our millimeters of mercury are going to cancel, our liters are going to cancel, our Kelvin are going to cancel, and then we're going to be left with moles in the numerator. That's what we want. We're looking for N, the number of moles. And this ends up being 0.0110 moles of hydrogen. I limited this to 3 significant digits because the volume only had 3. Let's try another example of an ideal gas law problem where we solve for volume. This time we have a pressure of 1 atmosphere. We have an amount of gas of 1 mole. We have a temperature of 0 degrees Celsius, which is 273.2 kelvins. And for R, we're going to choose the one that's 0.08206 liters atmospheres per mole Kelvin, because we are dealing in atmospheres as our unit of pressure. This time we want to solve for volume. So volume would be nRT over P. So we have N being 1 mole, R being the 0.08206 liters atmospheres per mole Kelvin. Then we have a temperature of 273.2 Kelvin and a pressure of 1 atmosphere. And that comes out to be 22.4 liters. This is the approximate volume that 1 mole of gas would take up at 1 atmosphere and 0 degrees Celsius. So this is what a mole of gas is at standard temperature and pressure. So the pressure to me seems pretty standard, 1 atmosphere. This isn't a temperature I like to have be too standard. I don't really like having room temperature be 0 degrees Celsius, but for some reason that was picked as the standard temperature as well. And so a lot of times people talk about a mole of gas being 22.4 liters under typical conditions. And even for illustrating a mole, a lot of times high school chemistry classrooms will have a beach ball that's 22.4 liters. It just makes kind of a fairly large size beach ball is what this volume takes up. So if the problem mentions that it's standard temperature and pressure, we can use the relationship that 1 mole of gas equals 22.4 liters of volume. So here we want to figure out how many liters of chlorine gas correspond to 8.76 grams of aluminum. So our relationship between aluminum and chlorine is a molar relationship. We have some coefficients here, 2 moles of aluminum and 3 moles of chlorine. And we can get to moles from aluminum from grams of aluminum. So it looks like our game plan is to get from this 8.76 grams of aluminum to convert that to moles of aluminum. And then we can convert that to moles of chlorine because we have that relationship told to us by the coefficients. And then we're going to take the moles of chlorine and figure out how many liters of chlorine we have. And we're going to, for here, use the molar volume, the fact that a mole of gas is about 22.4 liters. So let's go ahead and do that. We have 8.76 grams of aluminum. If we look up the molar mass, aluminum is 26.98 grams per mole. And then 2 moles of aluminum react with 3 moles of chlorine. And if we're at standard temperature and pressure, 1 mole of chlorine should be 22.4 liters of the chlorine. And that comes out to be 10.9 liters of chlorine is what you would need for that reaction.